Hello friends, welcome to the channel of Lavanya Healthcare. Let's continue our topic and we were about to start plane polarized light. As the name suggests, plane polarized light is a light which is polarized towards a single plane. It is a light wave in which all photons have the same polarization, that is only one direction. Light waves are electromagnetic in nature, we all know that, and they are composed of both electric and magnetic properties. In nature, the orientation of such fields is along various planes. Means either it will be having right direction, left direction, upward, downward, somewhere, but it will be having some direction. This is compulsory for all electric and magnetic fields. In other words, light waves oscillate or vibrate in various planes. This is known as unpolarized light. It is not having any polarization or poles. Passing an unpolarized light through a polarizing filter, which is Nicol prism, allows the vibration specific to only a single plane to pass through, thereby achieving what is called a plane polarized light. And the process of converting an unpolarized light to a polarized light is known as polarization. Now, the chiral molecules are always optically active. This implies that when this plane polarized light passes through a chiral molecule, then it interacts with the molecule in such a way that angle of plane of oscillation rotates. A plane of enantiomers always rotate plane polarized light to an equal but opposite degrees. For example, like we have discussed about D and L glucose. So D and L glucose both will be having same angle of rotation with opposite signs. Dextrorotatory will have a positive sign of rotation and levorotatory has a negative sign of rotation. Most biological compounds are chiral, like sugars, amino acids, etc. So here comes a rule of thumb. The rule of thumb is chiral carbon centers are carbon atoms that are attached to 4 different substituents that are placed at the corners of a tetrahedron. Chiral carbon atoms are also referred to as stereogenic carbons. So this way there is a strong relation between the rotation of plane polarized light and chirality of the carbon atom. If a carbon is a chiral carbon, means it is having asymmetry, then it will surely rotate the plane polarized light to a certain extent from 0 degree. And we can call it optical activity. Now what is optical activity? Plus means dextrorotatory, minus means levorotatory. And since these isomers exhibit different optical activity, they are referred to as optical isomers. Configuration of each chiral carbon of 2 isomers, or we can call enantiomers, is systematically assigned using RS system of nomenclature. This method was developed by 3 chemists, R.S. Kahn, C. Ingold and V. Prelog, and is also called Kahn-Ingold-Prelog rules of naming enantiomers. There is no correlation between plus and minus and the R and S stereochemical labels, and R stereomer can either be plus or minus. And optical activity of R and S has to be measured experimentally with a polarimeter. And what is polarimeter? Polarimeter is the instrument by which we can measure the angle of rotation of plane polarized light due to the presence of a particular chiral carbon or chiral compound. So as we are going into the discussion of the R and S configuration, let us be clear how the spatial arrangement of tetrahedral carbon with respect to the plane of molecule is depicted. Before we assign RS system, the four groups attached to the chiral atom have to be arranged in a relative order of priority. I will be giving you the priority series at the last. The group with the highest atomic number is given the highest priority, means first number, and group with the lowest atomic number is given lowest priority, that is fourth number, because there are total of 4 substituents. Now we have to make sure that lowest priority group is pointing away from us. Away from us means from you it should be pointing away. It is attached to the hashed wedge in the 2D spatial arrangement. Now draw a curved arrow from highest priority substituent to the second lowest priority substituent. If the arrow turns in the clockwise direction, the configuration is labeled S. And what is the full form of S? S means sinister. It is a Latin word for the direction left. And if the arrow turns clockwise, then the stereo center is labeled R. R means rectus. In Latin, it is called right direction. Now, how are we supposed to proceed if the lowest priority group is not pointing away from us? In that case, we need to select any one of the two groups that are present in the plane of molecule and rotate the molecule about that axis and stepwise move as shown above. Okay, until and unless the lowest priority group is pointing away from us. Then priority number is assigned to atoms that are attached directly to the stereogenic carbon. So what happens if there are two substituents with the same rank? In such a case, simply proceed along the two substituent chains until you find a point of difference. So the four atoms attached directly to the chiral carbon, or we can say the stereo center. The importance of chiral drugs in the drug development space cannot be understated. 56% of the drugs currently in use are chiral molecules, and 88% of the last ones are marketed as racemates. Racemate means racemic mixture, means 50% of dextrorotatory and 50% of levorotatory compound. Although the enantiomers of chiral drugs have same chemical connectivity of atoms, they exhibit huge difference in their pharmacology, toxicology, pharmacokinetics, metabolism, actions, etc. Therefore, when chiral drugs are synthesized, much effort is put over for the rigorous separation of the enantiomers. This ensures that the only biologically active compound is obtained as the final product. The enantiomers of the chiral drug differs in their interactions with enzymes, proteins, receptors and other chiral molecules, and as you all know, our body is highly stereospecific in nature. So these differences in interactions in turn lead to the differences in biological activities of other enantiomers for their pharmacological activity, pharmacokinetics, metabolism, toxicity, immune response, interaction with the cell at the barrier layers, etc. Surprisingly, biological systems can recognize the two enantiomers as two very different substances because of the highly stereospecific nature of our body and the cells. So this is all about it. Let's discuss some more about the stereospecific nature and drug action in the next video. Till then, Bye bye.